Okay, we are now looking at the second case when the population standard, when the population variance is unknown. Okay, so here we have two cases as well. If the population standard deviation is unknown, but the sample size is greater than 30, then we use the similar formula that we used earlier. Okay, so if the population standard deviation is unknown and the sample size is greater than 30, then we use the same formula that we used when the population standard deviation was known, except where we have the standard deviation, the population standard deviation, we are going to put the sample standard deviation. Okay, so that's the difference. If the population standard deviation is unknown, but the sample size is greater than 30, then we use this same formula, but where there was standard population standard deviation, we're going to put the sample standard deviation. Okay. But if the population size, if the standard deviation is unknown and the sample size is less than 30, okay, so the population standard deviation is unknown and the sample size is less than 30, then we use the student t distribution. Okay, and the t value is just given by sample mean minus mu divided by sample standard deviation over root of n. And the degrees of freedom are n minus 1. This is a bit, how we find the t values is very similar to how we find the chi-square values. Okay. So here, remember, we are just saying that the standard deviation is unknown. So we are going to substitute the population standard deviation with the sample standard deviation S. Now, that is how we find the formula, for constructing a confidence interval. We're going to have that x bar minus t n minus 1 alpha over 2 s over root of n. Okay, so again this t n minus 1, the alpha over 2 is the critical value. We can again generalize the formula by just saying that it is x bar plus or minus margin of error, and the margin of error is given by that. Okay, so the t distribution is also just a family of distribution, and it depends on the degrees of freedom, and the degrees of freedom are given by n minus 1. It is similar to the standard normal, except it has flatter tails. Now let's see how we can use the t table to find the t value. Suppose n is 3, and suppose n is 3, then the degrees of freedom will be n minus 1, which is 2. And suppose we've been given an alpha of 0.1. Okay, if our alpha is 0.1, then our alpha over 2 will be 0.05. So to find the t value for this information, we're going to go first to the degrees of freedom, which is a 2, and go through that row until we meet the column of 0.05. Then where this row and column meets, that is our t value. Okay, so it is not difficult. What we have inside the table are t values. What you have there as column headers are just probabilities. Okay, so the t distribution actually approaches the z distribution as n increases. Let's have an example. Remember, in this case, we are constructing a confidence interval for the mean, but the population standard deviation is unknown, and the sample size is less than 30. Let's get to our example. A random sample of n equal to 25 has x bar of 50 and has a mean of 50 and a sample standard deviation of 8. Form a 95% confidence interval for the mean. So what do we find here? We see that the degrees of freedom will be n minus 1, which is 24. And the t value is just t n minus 1 comma alpha over 2. So we're looking for 95% interval, confidence interval. So what is our alpha? Our alpha is 1 minus 0.95. So that gives us a 0.05. But we have to divide our alpha by 2. So we get 0.025. Now go on your t table. Look for 24 degrees of freedom and follow that row until you are under the column 0.025. This is the value that you're going to find. Okay. On some tables you'll find it as 2.6. On some tables you'll find it as 2.064. Okay. So we then construct our confidence interval, but we have all the values in our formula. So this will just be, our mean is 50, the t value there is 2.0639, our s is 8, our n is root of 25. When we do that, we're going to find that we have our confidence interval between 46.68 and 53.30. Okay, we now look on how to construct a confidence interval for population proportion. Okay, so we have seen how to. So here, for us to construct a confidence interval for the population proportion, we're going to use the sample proportion. Okay, so the population standard deviation for a proportion is given by that, but it can be estimated. It can be estimated with the sample data, which is just a root of p hat multiplied by 1 minus p hat over n. So in this way, we're going to find the sample standard deviation. So that is the formula that we're going to use. And again, we have to find the critical value. You find the critical value, multiply by the standard deviation. Okay? Then, yeah, so that is our formula. So we have to remember that n multiplied by p multiplied by 1 minus p should be greater than 5. So that is the confidence interval for a proportion. Let's have our example. A random sample of 100 people show that 25 are left-handed. form a 95% confidence interval for the true proportion for left-handers. So we have that our n is 100 and well, our proportion is just 25 over 100, which is 0.25. So our confidence level is 95%. So alpha will be 1 minus 0.95, which is 0.05. Divide that by 2, find the critical value. Critical value will be 1.96. After that, we just insert in our formulas. In our formula, and we're going to find that our proportion is between 0.1651 and 0.3349. So that is our confidence interval. And it just means that we are 95% confident that the true percentage of left-handers in the population is between the numbers. Okay, so our final section of this topic is how to construct confidence intervals for population variances. Okay, so we are again going to use the sample variances, and here we assume that the population is normally distributed. We saw how to find the chi-square value when we looked at sampling distributions of sample variances. Now we find the chi-square again here. What this tells us that with the n minus 1 degrees of freedom, we can find the chi-square value using that, which is given by that formula. Okay. So the formula for construction of the interval for population variance is just this formula, n minus 1 multiplied by the sample variance divided by the chi-square value. Note here that we have the first one is the chi-square value across alpha over 2, and then we also have the chi-square value when we're using 1 minus alpha over 2. Okay, so you need to take note of this. This is how you're going to find the difference in the values, because the numerators are the same but the denominators are different. The other one has n minus 1 alpha over 2, and the other one has n minus 2 1 minus alpha over 2. So let's have an example. You are testing the speed of a batch of computer processors. You collect the following data. The sample size is 17, the sample mean is 3004, and the sample standard deviation is 74. Assuming that the population is normal, determine the 95% confidence interval for the population variance. Okay, so let's get our data there. N is 17, so the degrees of freedom are 16. Alpha is 0.05. Okay, so alpha over 2 will be 0.025. Now you need to go to your chi-square table and find these values. N minus 1 alpha over 2. So you just go straight to n minus 1 and the column should be 0.025, and where this meet, that is your chi-square value. Then you go to 16 again and your column should have the probability of 0.975, and that is your chi-square value. Once you get your chi-square value, put in your formula. You have 17 minus 1, 74 squared divided by 28, the other one will be divided by that. So you find that actually your variance will be between those values. Okay. Now, we now look into how to determine the sample size Okay, for the mean and for the proportion. Okay, so we already identified that the margin of error is actually just the reliability factor multiplied by the standard error. Okay, so in this case, this is for the first case when the population standard deviation was known. So this is how we found that this is the formula for the construction of a confidence interval. But what we note here is that what is circled here is just the margin of error. So the margin of error is just that value. We can make n the subject of the formula and we come up with the formula. Z at alpha over 2 squared sigma squared divided by margin of error squared gives us the sample size that we need for that particular margin of error and the level of confidence. Okay, so we need to know those for us to know to determine sample size. Let's have an example. If our population standard deviation is 45, what sample size is needed to estimate the mean within plus or minus 5 with 90% confidence? So we put across our formula. What we see here is that 90% confidence, we need to look for the Z alpha over 2. That is our critical value. So our critical value is just, in this case, our alpha is 0.1. So alpha over 2 is 0.5. So look for the Z value at alpha over 2, which is equal to 0.5. So we're going to find this 1.645. When then we square, our standard deviation is 45. We square it. The margin of error is plus or minus 5. So we also square it. We're going to find that the sample size required is actually 220. Okay, now for the proportion, we also remember that to construct a confidence interval for a proportion, we say Z alpha over 2 P hat multiplied by 1 minus P hat over 2. So we change the subject of the formula and we're going to find that N is actually 0.25 multiplied by Z alpha over 2 squared over margin of error squared. Now we have put a 0.25 here because it is what maximizes this equation, okay? Because we assume that this can only be up to 0.25 because p hat okay, so we assume that 0.25 is what maximizes the statement p hat multiplied by 1 minus p hat. Okay. So, because the sample and population proportions are usually known, okay, and then 0.25 generates the largest possible margin of error. So again, to determine that sample size needed for the proportion, you need to know the confidence interval, the margin of error, and estimate, which is P multiplied by 1 minus P. Let's have our example. It says, how large a sample would be necessary to estimate the true proportion defective in a large population within plus or minus 3 with 95% confidence. So we put in our data there We have we have the critical value being 1.96, the margin of error is 0.03, and the estimate is that 0.25. So insert in our formula and we're going to find that we actually need 1068. Okay, so I hope you got something, actually everything, and we'll end here. Please keep on studying. Wishing you the very best. Thanks.